record. All right. Can you see that okay on the left side?
Yeah.
Clear enough?
Mm-hmm.
Okay. All right, absolute value. I don't think we need to read any of this, to be honest. We don't. Let's talk about how to do this. Absolute values on inequalities. First of all, let's make sure you understand how to do this. If I say 2x is equal to 8, what does that mean?
X is 4.
Well, here's what it means. It means two things.
Mm-hmm.
It means 2x is equal to 8 or 2x is equal to negative 8. So it actually has two solutions. X either equals 4 or x equals minus 4. Notice that minus 4 works perfectly good, right? 2 times minus 4 is minus 8, and the absolute value of minus 8 is 8. So this is a true statement regardless of which solution you plug in. Okay. The way you do equations with absolute value is exactly the way I do it, including writing it horizontally. Why do I write it horizontally? Because I got to solve each equation, and we're used to solving equations vertically.
Okay.
Okay? So if I had x plus 5 equals 8, what does that mean? What two things?
It could equal negative 8 or 8.
Give me the exact two equations that it means. Yeah.
So
in other words, you never change what's inside the absolute value. That's what I'm trying to point out. Is that never changes to x minus 5 or anything. Always leave what's inside the absolute value alone and only change the sign on what it's equal to. So I can solve each of these to figure out what the answer is. Now, with inequalities, that's a little different. If I have that is less than 5, that means two things also. It means x is less than 5. In other words, the first thing that they all mean is exactly what's written without the absolute value sign. Or, now for the or part, you have to change two things. Don't change what's in the absolute value, but change the direction of the arrow and the sign on the number. So that's what that means.
Okay.
You with me?
Yeah.
All right, now we're ready to do these problems. So I've got 6 minus 2x, absolute value of which is less than or equal to 3. So let's solve this. Tell me what two things that means.
6 minus 2x is less than or equal to negative 3.
No?
And 6.
Remember, the first one is exactly what's written without the absolute value sign.
Okay.
Or,
so then the next one, 6 minus 2x is lesser than or equal to negative 3.
I change the direction of the sign.
Is greater
than or equal to negative 3. In other words, you're always changing two things on the second part, the second equation, or the second inequality. This always is going to mean two different inequalities. But the second one, you have to change two things. When it's an equation, you only have to change one thing, the sign on the number. But when it's an inequality, you got to change both. Now solve each one vertically.
Okay, so negative 2x is less than or equal to negative 3. So then divide that by negative 2, and then x is less than or equal to
Remember when you're dealing with inequalities and you divide by a
Oh,
negative number, you turn the direction around.
okay. So x is greater than negative
Huh? Not
3 over
negative anymore. It's
2,
negative 3
positive 3
divided by
over 2.
negative 2. That's a positive 3/2.
Okay.
Okay? Now let's solve this one over here.
So it would be negative 2x is greater than or equal to negative 9.
Okay?
And then it would be divided by negative 2, so x is less than or equal to 9 over 2.
You got it. That's the way you do it. Now, if they wanted me to graph that, you graph it strictly on a horizontal number line. Okay, I'll put 0 on there. So 3/2, we'll call that 3/2. 9/2, I'll put up here. And the way I would graph it is we got to be greater than 3/2 with a solid dot. We got to be less than 9/2 with a solid. You know the difference between solid and open.
Yeah, solid is when it's
Right,
equal
when it's
to.
greater than or equal. If it was just greater than, it would be an open dot. And it's everywhere in between. In other words, it's this or that, which defines this area right there. Now, they didn't ask us to graph it, but you probably would have to graph it in class. And I noticed that they do actually graph it in their examples. In other words, this one up here that they have prior to 14, they not only gave a solution, which was x is greater than -1, but less than 2, but then they graph it, and you can see the open circles, and it's between -1 and 2.
Mm-hmm.
Okay, so let's do the next one. Okay. I'll listen, you talk.
Okay. So 1/2 x minus 3 is less than or equal to 4. And then the other one is 1/2
Or,
x
don't forget the word,
4.
and there's a reason, because there's another word and they're different.
Okay.
These are always ors.
Okay.
What's the rest?
Or it'd be 1/2 x minus 3 is greater than or equal to negative 4.
Okay. I'll solve each one.
So 1/2 x is less than or equal to 7. And then, so x is less than or equal to 14.
Over here.
So 1/2 x is greater than or equal to negative 1. So x is greater than or equal to negative 2.
Yeah, notice here we never had to divide by a negative number, or it's divide or multiply. If you're multiplying by a negative number, you got to switch that direction also. Okay, and then on a number line, there's -2, there's 14, closed dots, every point in between. Okay. Why did they have all this explanation in between 15 and 16? They appear to be the same. Just reading what they have here. Oh, I know it's going to be different. We'll see when we get our what's different. It's not going to be a solid line. It's going to be like they show here, You see, I don't know if you can see where I'm pointing, about halfway through the page with that number line.
Yeah.
It's not between -2 and 2. It's everything greater than 2 or less than 2.
Okay.
And that's what these are going to come out to be. And that's why they've separated it by all of this explanation. Two problems they just gave us were a finite set. Okay. Go ahead.
So 5 minus 2x is greater than or equal to 3, or 5 minus 2x is less than or equal to -3.
Solve each one.
So -2x is greater than or equal to -2. So then the x is less than or equal to 1.
On the right side.
-2x is less than or equal to -8. So then x would be greater than or equal to 4.
I like your arithmetic skills. They're good. Usually when I get students that are reviewing algebra, their problems are all in the fact that they don't know their multiplication tables and they don't know how to add and subtract positive and negative numbers. But you do. And the fact that you do is great.
Cool. Already a step ahead of the game then.
Well, it means we don't have to work on that. Now, if I graph this, there's 1, there's 4. Notice that my graph goes that way and that way. So I have an infinite number of points that satisfy the equation or the inequality, but not any point between 1 and 4.
Mm-hmm.
So my answer, if I had to put this, are you familiar with interval notation?
Yeah.
Okay, so interval notation would be what for this solution set? Start from left and go right.
So negative infinity, then we go to...
Look at the graph.
Yeah.
What's it go to?
It goes to 4.
Start from the left.
Okay.
Negative infinity to 1. I need a bracket or a parentheses around the 1?
Bracket.
Because it can be 1. Notice 1 satisfies that. The absolute value of 3 is greater than or equal to 3. That's a true statement. And in combination or in union with what?
Parenthesis 4 infinity.
That arrow means it goes out to infinity. It goes on forever.
Yeah.
Now, infinities always have parentheses.
Oh, and then the bracket would be by the 4.
And there's your answer for the solution set in interval notation. This is also fine. If you're not using interval notation, you could put that, or you could draw the solution set like that. That's also fine. But if you have to put it in interval notation, that's the only answer that's proper.
Okay.
Okay? And the only difference on 17, it's not really going to be any different. It's going to, I guarantee it's going to have a solution much like the last problem. In other words, it's not going to be a finite segment of the number line. It's going to be from negative infinity to some number, and then from another number to positive infinity.
Okay.
Okay. I don't mind skipping some of these if I see you get it. Now, it also, there's something to be said for practicing. Let's just do them all.
Okay.
Because it looks like what they're doing is giving us one or two problems of each type. And so if I have to explain how to do the first one, then it's good that you do the second one on your own completely.
Okay. So this one would be 7 minus 2/3 x is greater than 2, or 7 minus 2/3 x is less than -2.
Solve each one.
So then -2/3 of x is greater than 5. And then
Minus 5.
oh, yeah, wait, no. Yeah, minus 5.
Okay, and then x.
Um,
Now, do you know
so
how to
x,
solve this in one step? In other words, you could multiply both sides by 3 and then divide both sides by -2. But it's really more efficient to just multiply by the reciprocal. You know what I mean?
okay,
In other words, what I'm going to do is I'm going to multiply that by -3/2. And that will
okay,
leave x all by itself.
okay.
But I'm multiplying by a negative number. Got to turn that
Let's
around.
switch it.
What's on the right side?
Um, so multiply that. Would be 15 over 2.
Uh-huh. Or
Or, um, -2/3 x is less than -9. And then multiply the reciprocal. So x is greater than, so 9 over 1. So it would be 18.
negative, well, hold on. You're multiplying by the reciprocal. So
Oh, okay.
27/2.
Yeah.
Okay. It's fine to do it in one step, but make sure you multiply by the reciprocal, not by the same thing. Notice that
Okay.
I don't get rid of the 2/3 if I multiply by 2/3. Only way I get rid of that coefficient is by multiplying by -3/2, which means I got to multiply the right side by the same thing.
Understood.
Yeah, and now on a number line, again, here's 15/2, here's 27/2. Open or close dot here.
Open.
And which way does the line go? Left or right?
On that one, it goes to the left.
And this one, open or closed, and which way?
Open and to the right.
And now give me the interval notation for the solution set.
Negative infinity to 15 over 2.
Yeah, I made a mistake. I put the parentheses in there for you, but it should be parentheses, right? In other words, open
Okay.
circles translate to parentheses, closed circles translate to brackets.
Okay.
Okay.
And then on the other one, it would be 27 over 2.
First of all, parentheses.
Yeah, and then 27 over 2, infinity, parenthesis.
Okay, good. And that's 3 different ways to express the same solution. That, there's the curve, and there's the interval notation. What was that, 17?
Mm-hmm.
Okay. Straight lines are called linear equations. The most standard format is y equal mx plus b. Not sure why they tell you that, because then they proceed to give you the very first problem, which is not a linear equation. In other words, y equals x squared plus 1 is not a straight line. Only things that are straight lines are where x is to the 1 power. That makes it linear, like y equal 2x plus 1. That's linear. That I could draw a straight line. And this just tells you that if you don't know how to draw it, you can make a table of points. Okay? But you should have a good idea how to draw any of your elementary functions. Like, you know how to draw y equal x squared.
Yeah, it's just the line through the middle of the diagonal. Parabola.
So the parabola, its vertex is at the origin. That's y equal x squared. Okay? That's one of your 10 elementary functions. You want to know what the graph of every elementary function looks like. And as we get to them, I'll draw them if you don't know what it looks like. Now, to graph y equal x squared plus 1 is a transformation of the elementary function. What kind of transformation is it?
It's just going left and right. So it would go...
It's vertical.
Oh, it would go up and down.
Remember that it's outside the function. Anything that's outside, you got 3 vertical transformations. They're all outside the function. You got 3 horizontal transformations. They're all inside the function. And what I mean by that is if I had y equal x plus 1 quantity squared, that would be inside the function. That would be a horizontal shift. But when it's outside the function, that's a vertical shift.
So it would just go up one, or the middle would go.
I'm going to take my curve and just not change its shape at all. It's just going to go through that point right there, which is 1. And that's how you're going to want to graph all of these. Although the way it's kind of pointing you to is that you'd make a table for every one of them, draw the dots, and then connect the dots. You know what I mean by that?
Yeah.
In other words, that's what they've done in their example. They've chosen 5 numbers for x, figured out what y is. First dot's going to come at -2, -3. That's that dot there. Next dot's going to come at -1, -1. So you end up with 5 dots. Connect them. Got a straight line. You end up with the graph. That's a hard way to graph stuff. Especially, it's not even an easy way to graph a straight line. But it's definitely not going to be an easy way to graph parabolic equations or hyperbolic. 19 is hyperbolic. 20 is hyperbolic. 21 is quadratic, which means parabola. And 22 is quadratic, but it's not y equal x squared, it's x equal y squared, which means it's a horizontal parabola, not even a function. But we can still graph it. And I'll go through each of these when we have time. We're not going to have time to do all of these today. We'll do 18 and then we'll do 19, and we'll stop at 19.
Okay.
First of all, what's the parent function for 19?
Is it just a line?
1 over x. That's your most basic hyperbola. this.
Okay.
Both of those are asymptotic with the x and the y-axis both. In other words, if I go to positive infinity on the x-axis, I'm still not going to be touching the x-axis. It's just going to get closer and closer and closer. Notice that as x gets bigger, y gets smaller. In other words, 1 over 10 is bigger than 1 over 100, which is bigger than 1 over a million.
Mm.
And same thing on the negative side. So this is your standard hyperbolic equation. It's got a horizontal asymptote and it's got a vertical asymptote. Well, the function they gave us was y equals 1 over, I'm going to call it x plus 1 instead of 1 plus x.
Okay.
Now, this is inside the function. It's an adjustment inside the function. And the way I can kind of tell that, just not to make it too complicated, but if I call my y equal 1 over x, let's call it f of x equal 1 over x. Same thing, right?
Mm-hmm.
Well, this thing over here, if this is if f of x is 1 over x, then this function is f of x plus 1. Right?
Okay.
In other words, you take whatever's in the parentheses and you plug it in for x. So if f of x is 1 over x, then f of x plus 1 is 1 over x plus 1. So when I see that function there, I know I'm doing something inside the function because of that. Because
Okay.
I can put everything inside the parentheses. That means it's inside the function. So it's a horizontal shift. Which way?
Inside the function, it go right. One.
Actually, it's left. If it
Oh,
was,
because it's plus 1. Sorry. Yeah, it go left 1.
always x minus h. You'll notice that every time you have a h involved, it's x minus h, and it's y minus k. And it's always subtracting it, and then h is a positive number, it's a shift to the right. But there's an easier way to figure it out, whether it's a shift to the right or the left. And that is, there's a little tip there. Consider x is minus 1. Well, could x be minus 1?
Yeah.
Dividing by 0. Can never divide by 0.
Okay.
Which, what that tells me is that my vertical asymptote must have moved. In other words, when I do a horizontal shift, I shift my vertical asymptote. So the vertical asymptote shifted left. I know it has to go through minus 1.
Mm-hmm.
Well, didn't do anything to my horizontal asymptote, so it's the same place. Now I'm going to draw my hyperbolic function relative to those two asymptotes. So it's going to look exactly like this. See what I did?
Okay. Mm-hmm.
That's how you graph those, and then take away the original, not needed. In other words, the way you graph hyperbolic functions is to draw your asymptotes first, laying out a grid, and in the upper right grid goes your curve, and the lower left grid goes your curve. So that's how you do transformations of hyperbolic functions.
Okay.
All right, Madison, I will talk to you tomorrow, I think, right?
Yep.
I will talk to you then. Have a good night.
You too.
All right, bye-bye.